Welcome to the second part of this module. Let's continue with the examples of supervised learning. 3. Logistic regression. A detailed explanation. What is logistic regression? Logistic regression is a supervised learning algorithm used for binary classification problems, where the outcome variable has two possible categories, e.g., yes, no, 0, 1, spam, not spam. It predicts the probability of an event occurring based on one or more independent variables. Since probabilities range between 0 and 1, logistic regression applies the sigmoid function, logistic function, to map predictions to this range, transforming a linear equation into an S-shaped curve. Why use logistic regression? Many real-world problems in agriculture involve binary outcomes, where decisions are made based on yes, no, or 0, 1 classifications. Some examples include 1. Crop disease detection. Binary outcome, diseased, 1, versus healthy, 0. Use case, using image recognition or sensor data to classify whether a plant is affected by a disease. 2nd, pest infestation prediction. Binary outcome, infested, 1, versus not infested, 0. Use case, identifying whether a particular crop field is at risk of pest attack based on environmental factors. 3rd, soil fertility assessment. Binary outcome, fertile, 1, versus infertile, 0. Use case, determining if a soil sample is suitable for planting based on nutrient levels and pH. 4th, irrigation need prediction. Binary outcome, needs irrigation, 1, versus no irrigation needed, 0. Use case, using soil moisture sensors and weather data to decide whether irrigation is necessary. 5th, weed detection. Binary outcome, weed present, 1, versus no, weed, 0. Use case, classifying whether a section of the farm contains weeds for targeted herbicide application. 6th, crop yield prediction, pass, fail. Binary outcome, high yield 1 versus low yield 0. Use case, predicting whether a crop field will produce a high or low yield based on soil conditions, weather, and past data. 7th, livestock health monitoring. Binary outcome, healthy 1 versus sick 0. Use case, identifying whether an animal is sick based on body temperature, movement patterns, and feeding behavior. 8. Market readiness of crops. Binary outcome, ready for market, 1 versus not ready, 0. Use case, determining if harvested produce meets the quality standards for sale based on size, color, and moisture content. 9. Flood or drought risk prediction. Binary outcome, at risk, 1 versus safe, 0. Use case, predicting whether a farm is at risk of flooding or drought using weather forecasting data. 10th, seed viability classification. Binary outcome, viable, 1 versus non-viable, 0. Use case, testing whether seeds will germinate successfully before planting. Machine, SVM. How it works, dot. SVM finds the optimal decision boundary, hyperplane, that separates classes with the maximum margin. It uses kernel functions, e.g., linear, polynomial, RBF, to transform data into a higher dimension when necessary. Example in agriculture. Crop disease detection, classifying whether a leaf is diseased or healthy based on image data. Soil type classification, identifying soil categories based on chemical properties. How it works, dot. KNN is a non-parametric instance-based algorithm. It classifies a new data point based on the majority class of its k nearest neighbors in the dataset. Example in agriculture. Irrigation decision, predicting whether crops need irrigation based on similar past conditions. Livestock monitoring, identifying sick animals based on past health records. 6th, naive Bayes classifier. How it works, dot. Based on Bayes' theorem, it assumes feature independence and calculates the probability of each class. Works best with text classification and categorical data. Example in agriculture. Pest infestation prediction, predicting pest occurrence based on past weather and crop conditions. Market readiness of crops, categorizing produce as ready or not based on visual and physical attributes. 7. Artificial neural networks, ANNs. How it works, dot. Inspired by the human brain, ANNs consist of layers of interconnected neurons. They learn patterns through weight adjustments using backpropagation. Example in agriculture. Crop yield, prediction, using climate, soil, and weather data to estimate yield. Precision spraying, identifying the amount of fertilizer or pesticide needed for specific farm regions. எட்டாவது gradient boosting machineகள், GBM. How it works. GBM builds trees sequentially, where each new tree corrects the errors of the previous trees. Examples: XG boost, light GBM, cat boost. Example in agriculture. Soil moisture prediction, predicting moisture levels for efficient irrigation. Crop price forecasting, predicting future market prices of crops based on historical data. In general, each supervised learning algorithm has its strengths and weaknesses. The choice depends on data size, complexity, and interpretability. In precision agriculture, these models help with crop monitoring, yield prediction, disease detection, and decision-making, improving efficiency and sustainability. Now let's talk about data preprocessing. Data preprocessing is the process of cleaning, transforming, and organizing raw data into a suitable format for analysis or machine learning. In the context of agriculture, where machine learning is often applied, it ensures data quality and improves model performance. Missing values. Handling missing values is a crucial step in data preprocessing for machine learning. Missing data can arise due to various reasons, such as human error, sensor failure, software glitches, or even natural occurrences. If not properly addressed, missing values can negatively impact model accuracy, performance, and reliability. Causes of missing data. Human errors, mistakes in manual data entry or incomplete survey responses. Machine sensor failures, malfunctioning sensors in precision agriculture, weather stations, or IoT devices. Data corruption, loss of data due to network failures, file corruption, or storage issues. System constraints, data might not be recorded if certain conditions aren't met. Natural occurrence, in real-world datasets, some features may be inherently missing due to external factors. Handling missing values in machine learning. There are different techniques to handle missing data, depending on the type and extent of missingness. 1. Deletion methods. Remove rows, listwise deletion. If only a few rows have missing values, dropping them can be a simple solution. Not suitable when a large portion of the dataset is missing. Remove columns, column deletion. If a feature has too many missing values, e.g., greater than 50%, it may be better to remove it. Risk of losing important information. Second, imputation methods. Mean/median/mode imputation. Numerical data, replace missing values with the mean, average, or median of the column. Categorical data, replace with the mode, most frequent value. Forward fill/backward fill, time series data. Forward fill uses the previous value to fill missing data. Backward fill uses the next value to fill missing data. K-nearest neighbors, KNN, imputation. Predicts missing values based on the values of the nearest neighbors. Regression imputation. Uses linear regression to predict missing values from other features. Multiple imputation. Generates multiple datasets with different plausible values, then combines the results for better accuracy. Normalization. Normalization is a data pre-processing technique used to rescale feature values to a fixed range, typically 0, 1 or -1, 1 when negative values are present. This ensures that all features contribute equally to the model, preventing dominance by features with larger numerical values. Normalization is also known as min-max scaling. Why normalize data? Ensures uniformity. Different features may have varying scales. Normalization ensures consistency. Prevents bias. Machine learning algorithms, e.g., KNN, SVM, neural networks, may give more weight to larger values. Speeds up training, reduces convergence time for gradient-based models, e.g., logistic regression, neural networks. Improves model accuracy, helps prevent numerical instability in computations. When to use normalization. 1. When data does not follow a Gaussian normal distribution. 2. When the standard deviation is small and values are tightly clustered. 3. When using distance-based models like KNN, K-means, SVM, which are sensitive to feature magnitudes. Standardization. This is also called z-score normalization. It is a data pre-processing technique that transforms numerical features to have a mean, mu, of 0 and a standard deviation, sigma, of 1. This ensures that data is centered and follows a standard normal distribution, making it easier for machine learning models to process effectively. Z equals x minus mu divided by sigma. The table shows the difference between normalization and standardization in terms of features. We have come to the end of the second part of this module. Stay tuned for the other parts.